Hello, everyone. Today we are on day 24. We're skipping material on day 23. Just a couple little topics that we're not going to do. Um, so we're going to go right to day 24 today. I'm going to share my screen with you and pull up today's notes. And then I'll pull up the mini tab shortly and we'll take a look at that. So in day 24, what we're doing is we're going to take a look at multiple linear regression. This is MLR. So we're first going to talk about what makes something multiple linear regression, and looking at all the things that we looked at with simple linear regression, but now with multiple. So multiple linear regression is just the case where we have multiple predictor variables, so multiple x. So we still will only have one y, but now we're going to have multiple x predictors. And the y, same as before with simple linear regression, is numerical. And now the predictor can be numerical or categorical. We are not going to look at the categorical today. We're going to look at that next class. So today, everything is still all going to be numerical, and then we'll introduce the categorical side of it next lecture. Okay. So like we do for most of our classes, we get to know our data. So we have different things that we can do to just kind of get an idea of what's going on and get a feel for what the data is actually giving us. Maybe it's going to give us some insight for how our hypothesis test might work out, or a CI might work out, or just gives us just a clue what we're looking at, because some of the data, if we open it up, it's just overwhelming. There's too much going on and we can't see. I love this part for this type. A matrix plot is just a whole bunch of scatter plots. So it's going to be a whole bunch of scatter plots together, and we're going to pull that up on an example and we'll take a look. But it's going to be the scatter plot of y versus each x, and then each x versus all the other x's. And it really gives you a good idea about what's going on, right? So when we're looking in simple linear regression, the scatter plot really helps us see if there's some sort of linear relationship between x and y. So this does the same thing. It's just I have a whole bunch of them because I'm going to have a bunch of different x predictors. I mean, I might have two, right? So it could, but it's just multiple, more than just one. So that's what that's all about. And then we will get a correlation matrix. So it's the same thing as simple linear regression, except for instead of having one R value, correlation value, I'm going to have multiple, right? Because I have one for each X, Y combination, right? So I'm going to have a correlation value for each combination of X and Y. So we will get those in mini tab. So I have here how to get them and a little bit about them, but that's what we're going to do to get to know the data. So it's the same thing we did simple linear regression. And what we do is we kind of talk about something that has like that strongest relationship between X and Y. And that's what we try to mention. If I say mention something, I don't want you to talk about all of them. It's too much. Just pick out one that's strong. In this case, we're going to pick out the strongest ones. You might have two that are really strong, and you'll talk about both of them. And it's like one or two sentences. You don't need to go overboard with that. I want you to pay attention to this section right here. And what this is talking about is multicollinearity. And this is if we have a strong linear relationship between two x values, okay? So that just briefly talks about that for a moment. It's not a big deal. We just sometimes like to mention it if we see that. So you can always kind of jump ahead and do that if you see two x predictors have a strong value. Now we're saying like strong meaning close to like -9 to -1, or positive, or I'm sorry, -0.9 to -9, or +0.9 to +1. That's very strong. That's kind of what we're looking at. In that, you get from the correlation, right? Okay. Let's talk about the model, right? So this is what we're going to be using. This is what we need to do. So when we say regression analysis, I just want you to understand what we're saying is fit the model, make the model. I want you to get the equation. That's the model, right? And then everything else that comes with the output, it's just extra analysis for us. But when we say regression analysis, that means fitting the model, getting the equation of the line. That's exactly what it is. So it's just when we get that equation, we get a lot more with it, and then we can do more. So when we're doing the regression analysis, it's going to be the same thing as for simple linear regression. You can see here in the directions, we're going to go to stat, regression, regression again, and then fit the regression model. It's just my response, I only have one Y. And now for my predictors, I have all of them. So I'm going to put them all in, the same model, all at once. And the population model will look something like this right here. So my beta 1, x1. So this is my predictor 1, and then beta 2, x2, my second predictor, okay, all the way up to k predictors. So k right here is the number of predictors in the model. And then we have our estimated equation. So this is the equation made from the sample. This is what we're getting from Minitab, because that's what we're giving Minitab, the sample. It's the same equation. You can see it looks exactly the same. It's just we use B instead of beta. Beta is for the population, B is for the sample. And you can see everything is the same right here. Okay. The coefficients of the predictor, so B1, B2, all the way up to BK, that's what we're interested in. Now, in simple linear regression, we used to call this the slope because we only had one predictor, x, and it was the slope of the line, but not anymore. So in multilinear regression, we can't call it the slope because I have a whole bunch of them, right? I have however many predictors I have. So we just can refer to them as the coefficients. That's exactly what they are, but that's all we say. It's just the coefficients. We don't want to say the slope anymore because that would really not be accurate. So when we interpret the slope in simple linear regression, we would just say for each unit increase in my x and my y will also increase or decrease by my slope, right? It's the same interpretation, but now you have to add this little statement, holding all other predictor variables constant. Meaning, if all of these don't change and these all stay the same, then I can interpret B1 with this same statement. Okay, does that make sense? So as long as B2 and B3 and B4 all the way up to BK stay constant, they don't change, then I can interpret B1 this way, right? Because if these are constant, that means these are not changing. Any of these terms, the x's, they're not changing, they're not variables anymore, meaning this is my only variable. So as this increases, it will directly affect my y. So that is why we say that, holding all of the predictor variables constant. So all of these stay the same, and just this one is changing. But now I can do it for all of them. So if I want to interpret my predictor variables, and I have 3, I would have 3 statements. I normally ask for one in particular because you don't need to say the same statement over and over again. But what I'm looking for is holding all other predictors constant, then the statement about your traditional slope interpretation. Okay, so that shouldn't be too hard. That's really the same. It's just we're adding that little statement, but I just wanted to explain what that means for us there. Okay, so let's get down to the test of model utility. This is my test for significant regression. We did this in simple linear regression. What this is saying that the slope is something different than 0. So if the slope is 0, then we're saying our model's not statistically useful. And here it's the same idea. It's just now, again, we're not calling it the slope, it's the coefficients. So we're saying that all the coefficients all equal each other and they all equal 0. So you can see that here from my null. And at least one is not 0, and that means my model would be useful. So at least one of the coefficients is different from 0, then my model is useful. So again, we're going to use a shortened test process. Remember beta, that's the slope or the coefficient, right, in front of my predictor variable. So here, my real shortened test process, my null is that all the betas equal 0. My HA, at least one is not 0. I'm going to report the F, the degrees of freedom. Take a look at these degrees of freedom. It's the same thing we've been looking at. It's the degrees of freedom of the numerator comma, the degree of freedom of the denominator, right? Because F is a ratio. Right here you can see the actual calculation. So this is what it is. MSR divided by MSE. This is nothing new. We've been looking at this for a long time now with my F-test statistic, and I just did a little algebra to get this. Okay, so don't be overwhelmed with this. I just am showing it to you. So here I've got my p-value I'm going to report, and then I'm going to write my conclusion. My conclusion, same thing as we always do, right? We're not going to change that. So at the 5% level of significance, the sample data does or does not, right? So I'm going to pick one. It's depending if I'm rejecting my null or not. You don't have to show that part. I'm hoping we understand that if I say yes, then it does. If I say no to my question, if it's less than alpha, then no. Provide sufficient evidence to say that the model is useful. That's it. So it's either the model's useful or it's not useful, okay? Or you can say it's significant or not, so like you could either say it's statistically useful, significant, that kind of thing. You don't have to use my exact words. So that's my test for model utility. Whoops. And remember, we get this right from our Minitab output from when we built our model. We fit the model and we got the equation to line out. Okay. All right. I have a little bit of the output right here just to show you it's same as usual. Right here's my F-test statistic and my p-value. Here's my degrees of freedom. This isn't the full output, but it's just part of it. That's the part you're using. If we reject the null, then that means my model is useful. And of course, this goes back to like the ANOVAs with the multiple means. We found out something was different, but then we want to take it a step further and see what was different, right? Same idea here. We're finding out that the model is useful, but now I want to know, well, what is it that's useful, right? So which predictor is significant? Which predictor is useful? So we have a follow-up. Okay, so this is new because we don't have to do this with simple linear regression because there's only one predictor. So if it's useful, we know it's that predictor, right? Now with multiple, we have to figure out which one it is. So test for individual predictor significance. This is like a little follow-up, and it's not even, I say it's a test. You can use a test or a CI. It's like a one statement thing. So this is like where you're going to do your test for the above to see if your model is useful up here. And after, sorry, I'm scrolling all over. So after your conclusion, you're going to add another statement right after this. It doesn't have to be in the same conclusion. Like you can kind of space it out. Well, my computer's, oh, there it is. You can space it out if you want and then type it in here, whatever you want to do. So this is just one statement and you're going to just say which ones are useful. So you're going to look at your Minitab output and test for this. So if I'm doing a test, this means that I'm going to look at the p-value of each predictor, and if the p-value is less than 0.05, then it is significant. So that's easy enough, right? And then if it's not, if it's larger than 0.05, then it's not significant. Okay, so that's good to know. Or we can do a CI. So if we do a CI, I'm just going to scroll down here, and I could come back up. I think it's on the next page. I'll come back up to some of this and look at some of this, but I just wanted to go over the CI as well. The CI is when you get those expanded tables, right? So we did that last class, the expanded tables, you get this 95% CI. You would look at each predictor here. So I used an actual example. We're looking to see if 0 is in the CI, okay? So if 0 is not in the CI, then that means the predictor is significant. So you're either looking for not a 0 in the CI or a p-value less than 0.05 from your test. So that's it. So you could just, it's a quick look for either one, and then you're going to make a statement. So let me scroll back up so we can look at the statement. It's right here. So you can just say, you know, like with a p-value of maybe it's 0.025, this indicates that my predictor is a significant predictor, right? Or you could say, well, with a p-value of 0.15, this indicates that that predictor is not significant. And you just tell me what predictor it is, right? And the predictor variable. And you just have to just list it. It's not like you're writing a whole statement about it. Okay, so it's just a single sentence. And sometimes I'll just say which ones are significant, and then you just tell me. All right. So here's the p-values. It's in the coefficients box, part of the output, and you have your p-values. That's what you're looking at for each. You can see it right here. Each predictor. All right. So like I have this whole write-up and it's like over a page, but it's seriously, you just look at the output and you make a quick statement. It's a follow-up. It's not as bad. I just wanted to explain it on here as well as the video. This is what the write-up would look like if you had to do the write-up. I'm not asking you to do the write-up. I never ask anyone to do the write-up. It's not like I'm changing it. It's just that in case you wanted to know, this is what it's like. But we don't need to do that. There's no reason to do that. You can look at the output and get your results. Here's my CI interpretation. Maybe we just want to interpret the CI, and this is how we would interpret it, that 95% confidence that the population coefficient, because that's what we're calling it, I mean, that's what it is, of the predictive variable, so you just fill that in, is between this and this. Since 0 is not in the CI, we have evidence that the predictive variable is significant. So if I just wanted you to make a CI, that's exactly what you would do for me, okay? So I think that's kind of helpful there. All right, now that's if the model is significant, right? It's statistically useful if we reject the null and on our regression analysis. Now, if we want to know if the model is practically useful, this is where we look at our R-squared. So we did this on simple linear regression. And we just said as long as R-squared was greater than or equal to 75, we kind of used it loosely. Same idea here. So I'm not changing anything. It's just I'm now looking at R-squared adjusted. So when I'm looking at this R-squared adjusted, it's adjusted for the multiple predictors. So every time I add a predictor, that R-squared value will change based on how many predictors I have. So I just want you to know in multiple linear regression, we use the adjusted. It's just like the next one over to the right from the R-squared, same place in the output. Here's the calculation. We do not need to know this. Minitab will give us this value, but I just like you to know. Here's some interpretations and just a little bit about it. But what we're looking at is if that number is greater than or equal to 75, that tells us if it's practically useful. Like if would I use that equation of the line to predict some values. That's what you're looking at. This just gives us some examples of what the Minitab output might look like. So you can just take a look at that. But next, we're going to look at an example, and I'm going to start a new video for that. So I will be right back, and I will have a second video for the example.